Hello, and welcome to this presentation on the journey of a sample through an automated LC-MS workflow. My name is Robert Wardle, and I'm a senior scientist at Waters Corporation, where my role involves the development and support of applications on our LC-MS systems, and I also focus on automating these workflows. So today I will go through why you would want to focus on automation for LC-MS workflows. We will take a look at the Waters automation portfolio, and then we will go on a journey of the sample through this workflow, before finally looking at an example for a panel of steroid hormones, which is an application on Progestagens and Androgens. Once a sample is received into a laboratory for LC-MS analysis, the first thing we will need to do is perform some form of sample extraction. And the reason for this is that we need to remove matrix interferences. This helps to increase signal to noise by reducing chromatographic background noise detected in the mass spectrometer. The result of this is an increase in analytical sensitivity and provides better, more consistent quantification. Sample extraction also reduces variability associated with matrix effects, more specifically ion suppression and enhancement effects. This provides more consistent data and increased robustness of the LC-MS system through improved column lifetime and therefore reducing costs as fewer columns will be required for replacement. It also reduces downtime associated with cleaning of the system and its components, as the sample being introduced to the system is much cleaner. There is also the benefit of concentrating the analytes of interest, particularly those which are present at low levels that can be difficult to quantify. Of course, sample extraction can be time-consuming and laborious, and I know I have certainly had some long days in the lab where it's felt like my hand has fallen off like Arnie's. It's also prone to human error, especially when there are more complex extraction procedures required, and transcription errors are also possible, such as when manually typing results into a LIMS. This is why Waters has focused on automation and looking at ways to improve the workflow from sample receipt through to reporting of results back into a LIMS to minimize these problems. The evolution of the Waters LC-MS workflow started in the 2000s, where at this time and earlier, sample extraction was performed manually, generally with small batches of samples. Analytical systems were HPLC with tandem mass spectrometers such as the Waters Alliance and Quattro Micro, and informatics was only really used to control these systems. There was no sample tracking performed with no LIMS connectivity or automation. If we then wind forward to the 2010s, sample extraction was mostly still performed manually, but was moving to larger batches and having some liquid handling robot functionality. Analytical systems had moved on to UPLC with more sensitive tandem mass spectrometers, allowing for faster run times and the analysis of more complex analytes. Also, partial sample tracking was possible with the introduction of the TCAM file converter software, but there was still no LIMS connectivity. So now let's focus on our current solutions and then take a more in-depth look at how each of these can be applied to the LC-MS workflow. We have split products up into three categories based on sample throughput volume. For labs running a lower number of tests, products such as the Andrew Alliance Pipette Plus, which are electronic handheld pipettes, can provide a simple-to-use smart pipette system to help improve pipette accuracy and minimize human error. If solid phase extraction is performed, then the opto specialist can improve flow control when drawing samples through and diluting from the SPE plate with automated pressure gradients. The next step up into medium volume workflows looks at the Andrew Alliance Andrew Plus liquid handling robot, which automates parts or all of the sample extraction process, allowing for the analyst to perform other tasks whilst samples are being extracted. And then we come on to the higher volume workflows with larger liquid handling robots such as the Tecan Freedom Evo series or Hamilton Star products, which give the highest level of automation for the LC-MSIMS workflows and have the largest amount of flexibility. Another very important part of the LC-MS automation workflow is sample tracking, which helps to minimize transcription errors, and this is where the MassLynx LIMS interface and file converter tools come in, and these allow for connectivity between the LIMS, MassLynx, which is the Waters LC-MSIMS system software, and in some cases, the liquid handling robot software. And the role of these products is to transfer information such as sample ID, well position, and results. So now I am going to take you through our sample journey before we look at each of the products discussed and how they fit into this process. The journey begins with the request for the analysis of a sample. Multiple samples are typically batched together for the same analysis prior to their extraction and quantification. In the case of the Pipette Plus, no LIMS connectivity is possible currently, and therefore, once the lab is ready to perform the test, the work list with all samples to be tested is printed, and the analyst will retrieve these samples and perform the sample extraction. The analyst will then place the extracted samples onto the LC-MSIMS system for analysis. A MassLynx sample list can then be created by using the MassLynx LIMS interface software, which I'll discuss in more detail later. And with this, the sample ID from the LIMS is imported and the LC-MSIMS method parameters from a method-specific template are set. The analyst must then specify the well position or vial position of the samples, as with Pipette Plus, sample extraction is still performed manually. And once this is done, the sample run is submitted and LC-MSIMS quantification is performed. The final piece of the journey is the same for all LC-MS workflows. Once the data has been acquired, the batch is processed in Target Links Access software by the analyst. They can check that all acceptance criteria has been met, such as the calibration line correlation coefficient and QC sample bias being within the allowable limits. Target Links also has features to assist the analyst in this process, where data is flagged if it is outside of a preset tolerance limit. The data is then reviewed and approved before being sent back to the LIMS using the MassLynx LIMS interface. So how does Pipette Plus assist in this process, and what is different when compared to a simple electronic pipette? Well, they are browser-controlled electronic pipettes, meaning that the extraction method is programmed into the OneLab software. The analyst will then execute the method and the software will guide them step by step through the extraction. Furthermore, the volume of the pipette is set by the software automatically, and with the simple press of a button, the pipette will aspirate the reagent and then another press to dispense into the required container, which again is nicely displayed in the software, and you can just about see in the image shown. Of course, as a result of this, you will get improved lab productivity and reproducibility of results. If we compare this to the Andrew Plus for a medium volume workflow, the two are very similar. However, with Andrew Plus, the sample extraction is performed on a liquid handling robot as opposed to being done manually, which should help to improve day-to-day precision of results, reduce human error, and allow for the analyst to perform other tasks while sample extraction is taking place. Again, the journey begins with a request for the analysis of a sample, with samples being batched together. The analyst then retrieves the samples and either adds them to the deck of the Andrew Plus or transfers them into a 96 well plate for sample extraction, along with all reagents and consumables required as guided by the OneLab software. The extraction run will be executed, and once completed, the analyst places the extracted samples onto the LC-MSIMS system for analysis. The remaining part of the workflow is the same as we described for Pipette Plus, with a MassLynx sample list being created using the MassLynx LIMS interface software and samples quantified. Data is processed, reviewed and approved and sent back to the LIMS, again using the MassLynx LIMS interface tool. If we take a look at Andrew Plus in more detail, like Pipette Plus, it is controlled by the OneLab software, providing an easy-to-use visual interface to assist with the setup to run the extraction method and allows full traceability of protocols. Andrew Plus has the ability to perform a range of extraction techniques, such as protein precipitation, solid phase extraction, and liquid-liquid extractions, with its small footprint allowing it to be placed in a fume hood. The analyst will load the samples, which could either be in sample tubes or transferred into a 96 well plate, add the reagents and consumables, and then execute the protocol in the OneLab software. And then whilst the sample extraction run is taking place, the analyst's time is obviously freed up, allowing them to perform other tasks. And our final sample journey to discuss is for higher volume workflows, where a Tecan Freedom Evo or Hamilton Star or Starlet platforms are used. On the Tecan liquid handling robot, a batch of samples is loaded onto the liquid handling robot from a printed work list. Reagents and consumables are loaded and checked using laboratory SOPs, and the script is set to run. On the Hamilton Star or Starlet systems, there is the option to compare samples requested from the LIMS against those loaded onto the Hamilton system. And to do this, the MassLynx LIMS interface will create a file listing the samples for the analysis required. The analyst will load these samples, and the sample tube barcodes are scanned and compared to those listed in this worklist file. Any differences between the two will then be flagged to the analyst before the extraction run begins. The advantage of this is that it ensures the correct samples are extracted and analysed for that particular analysis. On both the Tecan and Hamilton systems, sample tube barcodes are scanned and tracked through the extraction process, and so the final location of all samples are known. Once the run is complete, a file is generated with this information present. In the case of the Tecan, a file converter is used to allow the sample ID and well position to be combined with a template containing the LC-MSIMS method information to create the sample list in MassLynx. However, for the Hamilton, all information can be generated using Hamilton's Venus software, and so the file can be generated directly with no need for a file converter. Once a sample list has been generated, the analyst transfers the plate containing the extracted samples into the LCMS system, and as with other workflows, samples are analysed, data processed, and reported back to the LIMS. So the Hamilton Star and Tecan Freedom Evo systems all have the ability to track samples through the extraction process from the sample tube barcode scanned by the robot. As you would expect, many different types of sample extraction methods are possible, depending on the deck layout selected, but the options available on each of these systems is almost endless, and I'm sure you could probably make some very precise cocktails as well if you wanted. These systems also have the ability to perform liquid level detection, which ensures that there is a sufficient volume of sample and reagents to perform the method, with the volumes set in the software. And to date, these liquid handling robots give the highest level of automation for a Waters LC-MSIMS workflow. And to get the sample ID and well position information from the TCAN into a format that can be imported into MassLynx, a file converter is used. Once the sample extraction run is complete, the TCAN EvoWare software generates an output file containing the sample tube barcode and final well position information. The file converter monitors the folder where this is saved, and any new files created are converted. To do this, the software will take the sample ID and well position from the output file and merge it into a method-specific template file, which contains the LC-MSIMS method information, and this file can then be imported into MassLynx. Looking at the MassLynx LIMS interface in more detail, once drivers are created and set up in collaboration with the LIMS provider, a connection between the two can be established. To import data from a LIMS, which is used to create MassLynx sample lists in the Pipette Plus and Andrew Plus workflows, a message is received from the LIMS for a particular test of a batch of samples. From this, the MassLynx LIMS interface combines the sample ID received from the LIMS with a method-specific template containing the LC-MSIMS method settings. The analyst will then simply need to specify the sample location and submit the run for analysis. And as I've also mentioned, the MassLynx LIMS interface tool can be used with the Hamilton system to compare sample IDs for a particular test, with the sample barcode scanned on deck to ensure that the correct samples are present for that extraction run. And then once data is analysed, processed and approved, the MassLynx LIMS interface can be used to send data back to the LIMS. Almost all information that is present in target links can be sent, where information is set up in the software, and once the target links file is processed and saved, it can be sent with the simple click of a button. This removes any need to manually input results back into a LIMS system, and therefore minimizing the risk of any transcription errors. MassLynx and target links also contain features to assist in the acquiring and approval process using MassLynx basic security. And in this, user privileges can be set. For example, groups are created by an administrator, which is typically a lab director, to allow for different permissions such as full system access for method developers and just run and process samples for analysts. And using the Windows operating system, a user account is created and then assigned to a particular group depending on their training and job role. All actions that are then performed in MassLynx are tracked, with an audit log being maintained. Target links also has features to require signatures and reasons for changes to integration, for example, and signatures for reviewing and accepting data sets. And so, to summarize, before I go through an example, Waters has seen that there is a need to simplify the LC-MSIMS workflow as much as possible, and this is why we have tried to address each of the bottlenecks in the process, from the request for a sample analysis right through to the reporting of results back into the LIMS, completing the circular sample journey. Automating the workflow as much as possible should help to improve robustness and precision of the results, minimize human error, and also minimize transcription errors. And so with my final few slides, I just wanted to go through an example where we have used this workflow to simplify the extraction and analysis of a panel of steroid hormones within our lab. And I think it nicely shows some of the features that I have discussed and also goes through a typical sample extraction method for LC-MSIMS. So for this testing, I performed a precision performance experiment where I evaluated QC samples at low, mid and high concentration levels. 5 replicates of each QC sample were extracted and analysed on each of 5 occasions, along with a calibration line on the Hamilton Star platform. Analysis was performed on a Waters Acuity UPLC I-Class Zevo TQS Micro LC-MSIMS system, and due to no LIMS present in our lab, as we are not a production site, we used a LIMS simulator tool to simulate this portion of the workflow. A test file was created using the MassLynx LIMS interface, which contained the method ID used to ensure the correct method is loaded, and also a sample ID information. This file was selected in the Hamilton method, as you can just about see in the top box of the image. The file is also used for the system to calculate the number of samples to extract, and then the first available well position in the 96 well plate is chosen, which allows for partially used extraction plates to be used. The Hamilton also allows for loading instructions, which guide the analyst through loading of the deck and also barcode checking to ensure that all consumables and reagents have been loaded correctly. For example, if the water reagent trough had been loaded into position 2 on the deck rather than position 1, an error message will be received for the analyst to change the position of that trough to be correct before continuing the run. All of these features are optional in the method, being displayed with a checkbox as shown in the image. However, it's also possible to lock these down within the script itself. And here is just an example of a load instruction from the method, where blue lights flash on the deck image to identify the location to load reagents, and a window describing where to load these reagents and the minimum volumes required to perform the extraction run. There are also lights that flash on the front of the Hamilton system, which display the correct tracks to add the reagents to. So in the example shown in the image above, you can just about see this would be on track 14 of the deck. For the sample extraction of this method, we followed our application note, which is also available on the Waters website if you would like further information. Following loading and barcode scanning, 100 microliters of sample was transferred from the sample tubes into a 96 well plate, where internal standard was added, followed by protein precipitation being performed. The liquid handling robot mixed the samples after each reagent addition, but centrifugation was performed off deck. Following this, the samples were returned to the liquid handling robot and solid phase extraction performed using an onboard vacuum system. Once the extraction run was completed, the collection plate was transferred manually into the LC-MSIMS for analysis, and the MassLynx sample lists were created from the output file generated directly by the Hamilton software. Extracted samples were injected using the Acuity UPLC I-Class FTN, and samples separated using an Acuity UPLC HSS T3 column with dimensions of 2.1 by 50 millimeters and a Vanguard pre-column. Detection was performed using the analytically sensitive Xevo TQS micro mass spectrometer, and a runtime of 5 minutes injection to injection allowed for the analysis of 12 samples per hour. Once data was acquired, it was processed in TargetLynx before statistical analysis was performed using Analyze It in Excel. The approximate hands-on time for the analyst in this steroid workflow to process 96 samples manually would take around 6 hours to complete, but utilizing the described automation workflow solution would only take approximately 2 hours of hands-on analyst time to complete, allowing for other tasks to be performed, such as the very important coffee breaks or even lunch. So now let's come on to the results. Concentrations of each steroid hormone in the QC samples are shown in the table. When samples are extracted on the Hamilton across 5 days, total precision and repeatability was less than 6.7% at all concentrations for all of these steroid hormones, showing the potential to provide a much more precise and robust workflow when compared to a manual approach, whilst also reducing the risk of human error and transcription errors. And so to summarise, we have gone through the reasons to focus on automation, where time-consuming and laborious steps can be avoided, and human error and transcription errors can be minimised, whilst also improving results across days with multiple analysts. We have looked at the current Waters automation portfolio for LC-MSIMS workflows and taken the journey of a sample through this workflow, before finally going through an example for steroid hormones. If you'd like any more information around what we have discussed today, then this can be found at waters.com/clinical. Or alternatively, feel free to contact me on the email address shown. And so with that, I would like to thank LabRoots for allowing me to talk to you today. And of course, I thank you for your attention and hope you have found this presentation useful. Thank you.